In 2017, scientists discovered an object passing through our solar system that was unlike anything else we had ever seen. For the first time, we discovered an object that originated from beyond our solar system, that was in the process of actively passing through our local neighborhood.
Massive, fast-moving visitor to our solar system may have been a probe sent by an advanced alien civilization.
At closest approach, it came inside even the orbit of Mercury and was discovered a mere 23 million kilometers from Earth, closer than any other planet ever gets to our world. Named Oumuamua, Hawaiian for messenger from the distant past, it has a number of properties that make it unlike anything discovered so far.
It looks very different from objects that we have found in the solar system.
Thus, this mysterious object that sailed unerringly through our solar system has been a source of endless speculation and fascination for years. But now, after years of speculation and intense study, scientists have made groundbreaking discoveries about Oumuamua, the mysterious object that has captivated the astronomical community and the public alike. Once thought to be an interstellar comet or asteroid, new research sheds light on its true nature, challenging our understanding of celestial phenomena and opening the door to new possibilities of what lies beyond our solar system. Join us as we dig deep into the latest findings, exploring how Oumuamua's unique properties and trajectory defy conventional classification, and what this means for future interstellar exploration. Billions of years ago, our solar system was an extraordinarily different place from what we know today. Earth had no multicellular life forms on it, no plants, no animals, no sexual reproduction. Saturn didn't yet have its rings, as the collision that destroyed one of its giant moons had not yet occurred. And the asteroid belt was much richer than it is today, full of rocky bodies that have long since been gravitationally ejected into interstellar space. Every solar system, if we understand how they form correctly, has a similar story. Small, rocky bodies, as well as the ice-dominated ones farther out, will get gravitationally kicked around by the planets and other objects around them. Many of these objects will get ejected, traveling through the galaxy until they randomly enter the vicinity of another alien solar system. And Oumuamua is such an interstellar interloper. When we saw this object passing through our solar system, it jumped out as being unlike anything else. Every object that we've ever found has an orbit with respect to our sun. Basically, there are four options as following: circular, with an eccentricity of 0, elliptical, with an eccentricity between 0 and 1, parabolic, with an eccentricity of exactly 1, or hyperbolic, with an eccentricity greater than 1. In fact, we've found objects in all four classes, with the hyperbolic objects corresponding to comets that were gravitationally kicked in such a way that they'll exit the solar system. They have eccentricities very slightly greater than 1, with values like 1,001 or so. But when we first found Oumuamua, we recognized it was something special. Unlike everything else we've ever found, its eccentricity was 1.2. Another way to understand why it was so extraordinary is to look at its speed on its way out of the solar system. If you were a Kuiper Belt object that interacted with another massive world out beyond Neptune or got perturbed by Neptune itself, you could gravitationally unbind it from our solar system, giving it a hyperbolic orbit. But its maximum speed upon exiting the solar system would be on the order of 1 kilometer per second. Same deal for an asteroid perturbed by Jupiter. It could reach speeds of a few kilometers per second upon leaving the solar system, but not greater. For Oumuamua, when it leaves the solar system, its speed will be 26 kilometers per second, an impossibly large number for something originating within our local neighborhood. In other words, it must have an extrasolar origin. This object had to come from interstellar space, from another star system that likely ejected it an unknowably long time ago. According to our best theoretical models, there should be many billions of these objects, at least for every single star in our own galaxy. it's extraordinarily likely that many of these objects pass through our solar system on an annual basis, but we've never detected them before. Until Oumuamua. As it came through the solar system, it passed interior to Mercury's orbit, extremely close to the Sun. Because our telescopes rarely scan very close to the Sun, we didn't actually discover it until it had crossed to the other side of Earth's orbit when it was already on its way out of the solar system. We found it when it was at nearly its closest point to our world, at a distance of just 23 million kilometers, around 60 times the Earth-Moon distance. It was moving incredibly fast at closest approach, reaching a maximum speed of 88 kilometers, about 3 times as great as the speed at which Earth orbits the Sun. And yet, for all of this, we were incredibly lucky to pull it out of the data. But unfortunately, as told, when Oumuamua got close enough to the Sun, it was moving fast, remaining for very little time in the relatively small region where it is visible to modern-day telescopes. As a result, astronomers were able to record data on Oumuamua for only a brief period of time. And now, they are working with what data they were able to gather over the course of just a few months to learn all they can about this strange interstellar interloper. At first, observers assumed Oumuamua, which is about 800 meters long and about 80 mims wide, was an asteroid. But in a Nature paper led by Marco Micheli, astronomers reported that Oumuamua was not moving as it should. Instead, it showed a really strong non-gravitational acceleration, which means its motion indicated that gravity was not the only thing dictating its path. And according to Karen Meach of the Institute for Astronomy at the University of Hawaii, there were a number of things that can cause acceleration in that direction. Meach and her team investigated at least 6 of those things that could cause the acceleration, throwing out several along the way, because they either required the object to be so very strange it wasn't plausible, or because the acceleration they produced didn't match what was observed. The team ultimately concluded the most likely one was comet outgassing, because we see that pretty often in comets. Outgassing is simply the process of gas and dust escaping from a comet as it nears the Sun and heats up, sublimating ices on the surface, turning them directly from a solid to a gas. As gas escapes, it gives the comet an extra push in the opposite direction, affecting its speed and rotation, giving it an extra push that deviates from gravitational effects. Oumuamua's motion was the same level of strength as you would typically see comets, so that didn't seem unusual. What was unusual is that no dust was seen coming from the object. When gas escapes from a comet, it generally carries surface dust with it, and the stronger the outgassing, the larger the grains of dust it can liberate. That didn't kill the comet theory, however. Meach says that even if the comet was devoid of small dust, large dust could have been coming off the surface and affecting its motion. And large dust is harder to see at visible wavelengths, where astronomers were looking. So, no dust was seen escaping Oumuamua, but what about gas? In fact, we didn't see any evidence of gas either, and that was actually strange, because astronomers expected a fair bit of gas to be escaping to affect Oumuamua's motion in the way that was observed. The caveat here is that Meach's team looked for CN gas, which is bright and easy to spot. According to Meach, CN is usually dragged off the comets in our solar system when water comes out, so it can be used as a proxy for water, which is harder to observe. But down to their detection limit, there was no CN at all seen, and that upper limit was strong enough that if there was that much water coming off, it says this comet's also unusual, chemically. After all, comets in our solar system can be pretty abundant in water. But again, if Oumuamua comes from another solar system, maybe that's not so surprising. Perhaps all these oddities are normal for something that formed somewhere else. At that time, the next question then becomes, where did this mysterious visitor form? Frankly, nobody really knows which star system Oumuamua originated from. Its slingshotting trajectory around the Sun tells astronomers that Oumuamua is not from around here. Comets tend to come from the Oort cloud, distant but still orbiting the Sun, and asteroids mostly come from a belt between Mars and Jupiter. Oumuamua couldn't have come from either place. It's the first interstellar object humans have seen so close to home. Its behavior and composition may have lessons to teach about the formation of planets and how things travel among them. Whatever Oumuamua really is, even if it's not aliens, is pretty amazing. So why do people hope it's aliens too? That's the metaphor part. That in addition to being a scientific marvel, Oumuamua might be a harbinger of a grander, numinous universe. Before it showed up, scientists thought interstellar objects were vanishingly rare. As the great philosopher Douglas Adams once wrote, "You just won't believe how vastly, hugely, mind-bogglingly big space is. Even if we humans are not alone, that bigness makes running into someone else out there highly improbable." But the fact that Oumuamua crashed our ecliptic party suggests that interstellar objects are pretty common, on the order of stopping by once every 30 years or so. That's wild. Measurements of Oumuamua's brightness and reflectivity suggest an elongated shape, like a cigar, which some researchers think is the result of getting knocked out of some other solar system, while stretched by the gravity of a Jupiter-like gas giant. The questions about Oumuamua, though, are even more exciting. If it is an asteroid, why is it in a weird, comet-like orbit? If it's a comet, why doesn't it have a tail? Why isn't it outgassing like comets do? Why is a cigar-shaped, unidentified object accelerating in a way that doesn't seem quite natural? That's the kind of question that sends the minds of UFO hopefuls racing at unimaginable speed. After all, the cigar-shaped spacecraft is a classic design in science fiction. We have Rama, the Doomsday Machine, the heptapod shells, the Nauvoo Behemoth Medina Station, Zentradi warships, the Infinity, and so on. Interestingly, this isn't just UFO subreddit agitation. Even real-live physicists with advanced science degrees are on board. As the Harvard astrophysicists Shmuel Bialy and Abraham Loeb wrote for the journal Astrophysical Review Letters, one possibility is that Oumuamua is a light sail, floating in interstellar space as debris from an advanced technological equipment. Alternatively, a more exotic scenario is that Oumuamua may be a fully operational probe sent intentionally to Earth vicinity by an alien civilization. Few scientists rushed to defend Bialy's and Loeb's hypothesis. As an astronomer from another Ivy League school, Cornell's Carl Sagan once put it, extraordinary claims require extraordinary evidence, and no one is flying to Oumuamua anytime soon to find out. It has left the building, where building equals solar system. Loeb, one hastens to point out, has a targ in this hunt. He is chair of the advisory committee for Breakthrough Starshot, a program to build a solar sail-powered spacecraft like the one Loeb thinks Oumuamua could be, funded by the Kremlin-backed venture capitalist Yuri Milner. But that doesn't mean Loeb is wrong. As Loeb told the Israeli newspaper Haaretz, "Imagine if cavemen had been shown the smartphone you're using to record me. What would they have thought about this special rock? Now imagine that Oumuamua is the iPhone, and we are the cavemen. Imagine scientists who are considered the visionaries of reason among the cavemen looking at the device and saying, 'No, it's just a rock. A special rock, but a rock. Where do you come off claiming it's not a rock?' Look, it's not that scientists don't want to find aliens. Instead, they really do. Present-day astronomers are using sophisticated equipment to listen farther and peer deeper into the universe than ever before, to find evidence of our cosmic neighbors. From detecting unexplained radio signals to investigating the atmospheres and liquid water on distant worlds, how are scientists searching for signs of extraterrestrial life? Well, first off, you have to know that for an alien-seeking scientist, life means any living form, including microbes. And even the smallest microbe living on a distant exoplanet, a planet orbiting a star other than our sun, could still broadcast a chemical signal that would be visible to sensitive telescopes in the form of atmospheric gases that probably wouldn't be there in the absence of life. One of the atmospheric gases astronomers are searching for in exoplanets is oxygen, which is plentiful in Earth's atmosphere because it is continuously being replaced by plants through photosynthesis. However, the presence of unusual atmospheric gases doesn't necessarily mean that something living is generating them, Lopez Morales added. For instance, sulfur molecules could come from active volcanoes. For oxygen, there are at least 2 or 3 ways to produce it that involve irradiation in the ultraviolet light coming from stars. But we know that oxygen appeared on Earth because life appeared on Earth. Of course, even if these chemical signatures can be detected, there's no way to tell what forms of life are producing the signal. And what type of exoplanet is a good candidate for life? Our familiarity with our own world nudges efforts toward those that resemble Earth, a rocky planet with a thin atmosphere with surface water. Sadly, right now we can tell, for some planets, if they are rocky, based on planet size and planet mass, which gives average density. But we can't yet tell if a planet has liquid water. So what else makes an exoplanet a promising candidate? The short answer is anything close by. For an astronomer, that means less than 30 light years away, which would enable humans to actually visit the world where life was detected. Now, 3 faraway moons, warmed by the gravitational tug and pull of the giant planets they orbit, tempt scientists with their promises of alien life in their oceans. Jupiter's moon Europa, where a salty sea containing more water than Earth's oceans sloshes beneath an ice shell, and Saturn's moons Enceladus, a small ice-encrusted world with a global ocean that erupts through fractures in its south pole, and Titan, with its unearthly terrain of liquid hydrocarbon lakes on its surface, and an ocean nestled within its interior. Observations suggest that each moon has the chemistry, water, and energy needed to support life as we know it, and maybe don't know it. We might soon learn if these seas are inhabited. A European Space Agency spacecraft called JUICE is on its way to the Jovian system to surveil the giant planet and its icy moons, including Europa. Late in this year, NASA's Europa Clipper spacecraft will also set sail for Europa on a quest to solve the mysteries of its crust and salty sea. And later this decade, the U.S. Space Agency's Dragonfly mission will send an octocopter to Titan, carrying a suite of instruments that could detect signs of life on the hazy moon's surface. Missions to Enceladus are being planned too. It, as says Morgan Cable of NASA's Jet Propulsion Laboratory says, is a really exciting time to be a planetary scientist. We could, for the first time in human history, find life somewhere else. But scientists aren't just looking for signs of extraterrestrial life. They're also listening for them. Nearly 3 decades, SETI, the Search for Extraterrestrial Intelligence Institute, has conducted research to understand the origins of life in the universe and to detect and analyze evidence of life emanating from places other than Earth. This effort includes investigations of microbial life within our solar system, such as on the surface of Mars or under the icy crust of Jupiter's moon Europa. SETI scientists are also monitoring the universe for signals in light or radio wavelengths that originate far away and could be signs of technologically advanced alien life. Theoretically, anyone doing regular radio astronomy, gawping at supermassive black holes for instance, could stumble upon one of these seemingly non-natural radio signals. But it's very unlikely. This sort of radio astronomy requires opening your instrument's mechanical ears to a huge range of frequencies. Looking for a radio techno signature means very carefully searching for signals amid the storm of natural noise. Fortunately, contemporary radio SETI searches levy the power of supercomputers and, increasingly, machine learning programs to simultaneously twiddle the dials of many different radio receivers, scouring for narrowband signals of interest. But lest we forget, space is gargantuan. Even if signal searches are more efficient these days, there's a lot of space to peruse. And most SETI researchers won't always do targeted research. For example, listening in on tranquil stars known to have potentially habitable rocky worlds orbiting them. Either way, as Jean-Luc Margot, a radio astronomer and technosignature researcher at the University of California, Los Angeles, says, "You don't know what an advanced civilization would do. They might build a radio beacon far from their homeworld, perhaps around a more hostile star, one they monitor remotely. Thus, the best approach is to look over the entire celestial sphere. If we are lucky, there may be a way to cut some corners. The most abundant stuff in the universe is hydrogen. Hydrogen gas is everywhere, and it naturally produces radio emissions at a specific frequency, 1420 millimassigmers. Other astronomy-practicing civilizations would almost certainly know this, and realize that other civilizations would also know this. So why not broadcast a transmission at that exact frequency? That's because even if that turns out to be the case, humanity's radio transmissions are obfuscating our efforts to look for the alien equivalents. Earth itself, and the many satellites orbiting it, generate a hurricane of radio waves. Sometimes, SETI researchers can pick up signals from space that are our own robotic spacecraft, or terrestrial signals bounced back from the moon. That's why some researchers are, ambitiously, calling for a SETI-focused radio observatory on the far side of the moon, which would avoid much of this noise, at least while the soon-to-be permanent human presence on the lunar surface remains small. But let's say you can rule out humanity's own radio interference. Scientists must then determine it's coming from somewhere else in space. One or a handful of radio observatories could be used to get a decent idea of where that signal was coming from. But if you use a huge number of radio dishes at once, the 64-dish Meerkat radio telescope in South Africa, for example, or even combining multiple observatories and arrays across the planet, you get a major boost in sensitivity that could allow you to locate the planet around a star from which the signal is broadcasting. Tick all these boxes and you have something extremely promising on your hands. But it can get even better. If the signal changed its structure during the transmission, something known as modulation, then that would blow everyone's socks off. We would know that it was also conveying information. This is the difference between hearing a constant dial tone on the phone versus hearing hold music or someone speaking. And as is often said, seeing is believing, and there is a chance that our first techno-signature will come about not by listening to the universe's radio stations, but by peering down the sights of a telescope. One way astronomers search for other planets is the transit method. If a star's brightness temporarily dips, then something probably passed in front of it, as seen from Earth. If it dips in regular intervals and by the same amount each time, that's usually caused by a planet. If, during a transit, a star's light passes through a world's skies, then it carries information about the chemical makeup of that planet's atmosphere. Information that, with the right instruments, astronomers can decode. This is useful for all sorts of reasons, including working out if a world is potentially habitable to biology of any variety, or even to search for hints of possible biosignatures themselves. Chemicals that can be produced, sometimes exclusively, by life. This technique could also be used to find the pollution from an alien civilization. Nitrogen dioxide, for example, is made by forest fires, volcanoes, lightning, and other natural sources. But much of Earth's nitrogen dioxide comes from the burning of fossil fuels, particularly from road vehicles. Detecting that on an exoplanet may hint at the presence of a fossil fuel-burning civilization that has yet to move exclusively onto sources of futuristic clean energy, like nuclear fusion. Like many biosignatures with both natural and artificial sources, the detection of plenty of nitrogen dioxide wouldn't be a slam-dunk confirmation of an alien intelligence. Other chemicals would sound a clearer alarm, such as chlorofluorocarbons. These are found in aerosol sprays, packing materials, solvents, refrigerants, and more. They ate away at the ozone layer before being broadly banned across the globe by the Montreal Protocol. There is no natural process that can produce chlorofluorocarbons, says Koparapu, the NASA planetary habitability researcher. It is not inconceivable that, as the James Webb Space Telescope is examining an exoplanet for biosignatures, it detects the presence of chlorofluorocarbons, SETI scientists are not just interested in the information carried by that starlight. They are also curious about the total amount of starlight they are receiving. When an object passes in front of the star, its apparent brightness dips, and it's possible the dip could be caused by something other than a planet, something much more implausible, but considerably more fantastic. Science fiction is full of alien megastructures, unfathomably giant objects like world-sized space stations, or colossal orbs surrounding stars to siphon off an almost endless supply of solar energy. There is always a chance that a transit reveals the existence of something decidedly non-natural around a distant star, a detection that could be followed up by targeted radio SETI work. Some transits have already raised astronomers' eyebrows. The chaotic, sporadic dimming around Tabby's star, named after an American astronomer who led the team that discovered the star's weird light fluctuations, for example, cannot be explained by the periodic orbit of a planet. Nobody can confidently explain the cause of these shenanigans, but various hypotheses have been suggested, including the shattered remnants of a planet, swarms of comets, and, yes, an alien megastructure, a type of optical technosignature. Although few scientists are betting on an extraterrestrial intelligence explanation, ongoing work has still to conclusively rule it out. While humans are fascinated by the possibility of discovering life on exoplanets, a team of researchers, seeing things from a different perspective, has pondered how life and habitability on Earth would look to an alien that would see our world as an exoplanet. How might they spy on us from afar? What would indicate to them that our planet is occupied? These questions go far beyond philosophical musings. There's a practical use for the answers as well. They'll be used to validate a forthcoming space mission, dubbed the Large Interferometer for Exoplanets, or LIFE mission, which will hunt for habitable exoplanets. The mission will be comprised of 5 spacecraft that form a single mid-infrared interferometer. They'll sit relatively close to the James Webb Space Telescope in an orbit around the Sun known as Lagrange Point 2, or L2. The primary target of life will be rocky or terrestrial planets that are similar in size and temperature to Earth. It's being built to pick up thermal emissions from these worlds and use their spectrums of light to deduce what elements and chemicals lie in their atmospheres. What's notable, rather than testing life's capabilities using simulated spectra of light associated with an exoplanet, the team behind this research decided to validate the mission by using the only planet upon which life has been discovered. That's our planet, Earth. The team took data from NASA's Aqua Earth observation satellite and used it to create the mid-infrared emission spectrum that would be expected from Earth if it was viewed as an unassuming speck from a great distance. At such a distance, our planet's beautiful mountains and blue seas would be indistinguishable. The team then averaged out the spectra and considered how the result would be impacted by seasonal fluctuations and our planet's geometry. The researchers accounted for 3 possible views, 2 from the poles of Earth and 1 from its equator. They also focused on data collected between January and July of 2017 to calculate seasonal variations. The team concluded that if life, or a similar instrument, were to observe Earth from as far away as 30 light-years, it would successfully determine our planet is a warm, habitable world. The crew also determined that atmospheric gases like carbon dioxide, methane, and water, all either important for or created by life, would be visible in our planet's spectra. A distant observation of Earth by a lifelike telescope therefore would reveal the conditions needed for our planet to support liquid water at its surface. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.